Hello. My talk will be on something slightly different. I develop X-ray phase contrast CT methodologies, and we're using simulations to assist us in this development. In this talk, I'm going to speak about one of our latest projects, which resulted in X-ray micro-CT data with isotropic spatial resolution and two-directional phase sensitivity. And I'm going to describe how we achieve this and how we use simulations to design the system. My talk will start with explaining what is 3-modal imaging and CT. Then I'm going to give a brief introduction of how our method works and the motivation. Then I'm going to speak about the sampling issue which results from using this technique. I'm going to speak about the proposed solution, the results, discussion, and finally the conclusions. So, what is 3-modal CT, imaging and CT, and why someone should bother considering it? I will explain this by showing 3 examples. As you all know, the conventional X-ray micro-CT, the contrast of the images, comes from the attenuation of the X-rays from the sample. But there are some cases that having additional information, additional to the attenuation, is beneficial. For example, 3-modal CT has been investigated for the evaluation of damage in fiber reinforced composites. And if you can see here, we have the three reconstructed slices. The first one is based on the absorption. The second is on phase, which is the refraction of the X-rays. And the third is based on what is called dark field, which is the ultra small angle scattering. So 3 different channels, and if we superimpose these 3 different information in this part, we can see that the information that is resulted from the 3 different channels is complementary. So the information that we get from phase and dark field can reveal some more things in addition to the absorption. Another example is the detection of microbubbles. For example, if our sample has some microbubbles, for example, 4.5 micrometers, are in this case, the attenuation images, so from the conventional X-ray micro-CT, or here the planar images, have the same contrast, whether the sample has bubbles or whether it doesn't have bubbles. Whereas the dark field image, we can see the difference in the contrast. And finally, again, this is planar, but we are developing it for CT. It has been investigated for melting of metals in laser additive manufacturing. And you can see here, as a function of time, with a 22 milliseconds of temporal resolution, from the time that the laser hits the powder and every 22 milliseconds, in the phase images and in the dark field, we are earlier being able to detect the formation of the droplet and its evolution. So this gives us a better understanding of such of the melting of metals in laser additive manufacturing. So there are some applications that can be benefit from 3-modal CT. Now, there are various ways where someone can get this additional information, and all the time you need to give something, you need to pay something in order to get these additional signals. For our method, it is based on beam structuring. So, this is a simple diagram which shows that we have the X-ray source, our sample, and the detector. Everything is the same as the conventional X-ray micro-CT. The only difference is that we introduce a mask right upstream the sample so that we can structure the beam, and instead of irradiating the sample with the whole beam, we irradiate it with beamlets. And by doing this, we are able to track each beamlet individually and see how the beamlet changes from the introduction of the sample. So what we can do is we can measure how each beamlet's intensity reduces, which we attribute this to attenuation, how the beamlet shifted, which we attribute this to the phase channel, and how each beamlet broadened, which we attribute this to the scattering. So another examples, this is X-ray micro-CT of a rabbit esophagus. You can see the three different channels: attenuation, phase, and scattering. This is the complex refractive index. The attenuation is proportional to beta, and the phase is proportional to delta. And we can see that because we know that delta can be orders of magnitude higher than beta, for weakly attenuating samples, we can have higher contrast to noise ratio. So overall, using this setup, using this method, we can get multimodality, increased contrast to noise ratio for weakly attenuating samples. With this method, it's important that the phase signal is quantitative because there are some other methods that don't give quantitative results. We can get sub-resolution sample inhomogeneities from the scattering. And another important thing is that this method is compatible with conventional sources. We don't need to do this at synchrotron. The second advantage is its spatial resolution. In conventional X-ray micro-CT, as probably you all know, the spatial resolution depends on the properties of the source, the properties of the detector, and the geometry of the system. Here, the spatial resolution is only driven by the sample mass characteristics. So how wide, how big are our beamlets? You can see that by using masks with smaller beamlets, we are able to detect smaller details. So the spatial resolution depends on the mask. And you can have with conventional source detectors better spatial resolution. Okay, so all this is good, but this comes with a cost. And the cost is the sampling issue. So here I'm showing a schematic diagram of two types of masks. With this mask, the white part is the aperture, is where the X-rays are passing through, and the black one is the absorbing septa. We structure the beam in one direction, but the part of the sample that is behind the black part, we don't get any information. So we undersample the data. And just to show this schematically, if this is a subset of the sinogram, and in x-axis you have the rotation angle of the scan, and in the y-axis you have the horizontal direction. With each frame we acquire, we have some acquired data, but a lot of data is missing because the sample is behind, is not irradiated by the X-rays. So with doing a conventional rotation-only scan, we have 1D undersampled sinogram. In order to overcome this, we do what is called dithering. So for each angle in the normal CT scan, we step the sample in small steps so that we can irradiate the whole sample with the X-rays, and then we move to the second angle. So with this method, we can get a complete set of the data, but the scan, it can only implement it as a step and shoot. So we put the sample at the position that we want, then we acquire. We move to the second step and we acquire. So this adds some overheads. And when we structure the beam with a mask that has circular apertures, then we undersample in two directions, and we need to do dithering, the movement of the sample, along the two directions, in x and y in this case. So our proposed solution. Again, I'm showing the two types of masks that we have been using previously. The other thing that is important is that depending on how you structure the beam, you can have different phase sensitivity. If we use a mask with slits, we can get phase sensitivity only along the x direction, which is the direction that we structure the beam. Whereas if we use such a mask, we can get 2D phase sensitivity, phase sensitivity along the x and the y direction. But as I said, this requires 2D dithering. This requires multiple frames per angle. This is what we have been using before, and our suggestion is to use a different type of mask, which from one hand it has circular apertures, so that we can have 2D phase sensitivity and isotropic resolution, but we have made the apertures to be as close as possible in the y direction, so that we only need to do dithering along one direction. And this reduces the scan times by a lot. And bonus point, this mask, this new design is compatible with cyclodal city fly scan, which I will mention at the end. This is the experimental setup, where we have the source, a flat panel detector, our sample, and few centimeters before the sample is the mask. And this is how the images at the detector look like. So we no longer see the sample, but we see the beamlets. And by reducing the sample, these beamlets reduced in intensity are shifted in two directions and broaden. And by tracking these beamlets, we can get the three different channels. Now, in order to assist us in the development of this method, we used a 3D wave optics model in MATLAB, which works like this. So we have the source and the detector, and we define them both in two directions in terms of their distribution, the source size, the energies, and the detector point spread function. And we do free space propagation from the source to the mask and from the mask to the detector using the Fresnel diffraction integral. And we also calculate the transmission of the X-rays from the mask and from the sample using the complex refractive index, so that we know how the wave is not only attenuating, but also shifted due to the refraction. And here is how the setup, how the simulation looks. In the mask plane, where we have the demagnified pixels, our sample, and these are the mask apertures, where the X-rays passes from them, but outside we have a full absorption. Here are some of the results. We have for the simulations. So in order to design this mask, we had to come up with how big the apertures would be and how close they will be in the two directions. The size of the apertures define our spatial resolution, so we don't want to make them very large, but also their period in x and y direction. They may make the beamlets to overlap, and we also don't want them to overlap, otherwise we won't be able to track them. So here is a simulated image at the detector of only the mask and the profile along the x and the y direction. So these are the beamlets that we are creating, and this is the experimental. So the good match of these two suggests that we have a good understanding of our source, of the detector, of the geometry of our system. And here I'm showing some examples of simulation, which is just a plastic sphere. This is the attenuation, the refraction in x, the refraction in y, and when you combine these two, you get phase. And the experiment with different plastic spheres. And by plotting a profile along the x and y direction in attenuation and phase, we can confirm that we have quantitative results. So as you can see in the simulations, there are two differences compared to the experiment. The one is that there is no noise, and the X-ray source was assumed to be monochromatic, which is not the case in the experiment. So we could do a further development of the model to have a better match, but the values are pretty similar. And we also compared the beta and delta, so these values are related to the attenuation and the phase channels. We compared the retrieved values with the nominal ones, and we had a very good match within uncertainties, which again confirmed the quantitativeness of this method. Finally, we did some scans, some CT scans of 3.5 millimeter diameter polystyrene granules, and you can see the attenuation. So this is the reconstructed volume and three different planes of the attenuation signal and of the phase signal. And by plotting a profile, we can see that with the phase, because these are plastic spheres and they have higher delta compared to the beta value, we have better contrast noise ratio. We also quantified the spatial resolution, and we found it to be isotropic, the in slice and the out of slice. And another example of a rat heart of a scan using this technique. For a scan that took 390 minutes. So again, I repeat that these scans, the 390 minutes is not the exposure time because we have some overheads. We have to move the sample along the X direction to acquire complete data sets. So overall, with this method, we have an increased contrast-to-noise ratio for weaklet and weight samples. We have quantitative phase signal. It is compatible with conventional laboratory sources, and we have increased anisotropic spatial resolution. However, we still need to do this 1D dithering. We still need to move our samples per angle. And this is not good for example, industrial applications. So our proposed solution, which is now under development, is to combine this with what we call the cyclodal CT, which is a combined movement of the rotation and the translation. So instead of translating the sample along the X direction in multiple positions for each angular position, we combine this movement in a rotor translation movement. I'm not going to go into details, but this method is fly scan compatible. So we can just continually rotate our sample and obtain a full sampling. So finally, some potential industrial applications. If we combine the new mask design with cyclodal CT in pre-commercial prototype scanners, we can consider this for sample inspection and quality control. And if we combine the new mask design with cyclodal CT in a conveyor belt, we may be able to do inline inspection, but we have to face some issues in order for this to be realized. As a conclusion, this method enables three-modal CT, which may be beneficial for some industrial applications, provides a mask-driven spatial resolution, 2D phase sensitivity, and with the new mask design, we only require to do 1D dithering, and under investigation is combining this new mask design with cyclodal CT. I've shown the importance of the wave optic simulations for designing the new mask effectively and help us understand our system better. And the demonstration of this method for industrial usage is underway in collaboration with Nikon X-Tech systems. This project was part of the Nikon UCL Prospective Partnership on next generation X-ray imaging. Thank you very much. Please let me know if you have any questions.